Hello everybody, my name is Walter, and this is episode 73 of my Redstone Commands Series. In this episode, I want to show you how you can use binary search to calculate the inverse of a given function in cases where this is not trivial to do otherwise. So to make this short, there are a lot of functions that fulfill at least the basic requirements for invertibility, but if you try to get an inverse function, you run into the issue that there is either no elementary formula for the inverse function at all, or there may be one, but it's very complicated and takes ages to calculate and a lot of processing power. In those cases, you may want to use a different approach, which I want to show you in the following. But first, let's have a quick look at the requirements for an inverse function. So we start with our function. So when we take our x value, we can determine the corresponding point on the graph. And that gives us our f of x value. Now, for the inverse function, we start with the y value, which is the f of x, get the corresponding point on the graph, and that gives us our x value, or inverse function of y value. So far so good. Now for this to work, the function needs to be continuous and strictly monotonic. In other words, if you have a function like this here, where the function has a sudden jump in the y value, and the y value you are looking for, or inputting into your inverse function, falls into this gap, then there is, strictly speaking, no defined x value for this. Now you could say, okay, this is the x value where the jump happens, but strictly speaking, mathematically speaking, it's not defined. So in other words, the function needs to be surjective or continuous and mustn't have any gaps. Furthermore, if you have a function like this here, then for some y values, you have multiple x values. So it could be either this one here or this one here in this example. Now we can get around this issue a bit by splitting the x value range and, for example, just looking at the first half here. Then you can get a proper inverse function, probably, and all works out. A bit more of a problem is if you have actual ranges where the y value is constant, so where the function is horizontal. So in this case, we can say whether it's this x value, this x value, this x value, or one of the infinite number of x values in between. And that is an issue you can't really get around even with splitting the ranges. It's not an issue if it's horizontal for just a singular point and the slope before and after is non-zero. It's just only really an issue if it's a range. In other words, the function must be injective, or you have to have a 1-to-1 ratio or relationship between y and x values. Now, I already talked about this a bit earlier. There are some functions that don't have any elementary formula for the inverse function, or at least not a nice one. A pretty common example are so-called transcendental functions, like for example x times e to the power of x, which has the inverse function, which is the Lambert W function, which has absolutely no elementary formula, but is very important in calculations and subsequently has been given its own name here. But even higher degree polynomials, like x cubed plus 2x, which fulfills the requirements for an inverse function, and actually has an elementary formula, as you can see here, is not something I would really want to implement using Minecraft commands because, well, you have square roots, you have cubed roots, you have x squared, and all of this, with all of the rounding errors involved, is a nightmare to do in Minecraft. So in those cases, using binary search is what I would go for. But how does this work? Well, let's have a quick look. We start again with our function. We also need our target y value. This is basically our input value for the inverse function. And we have to define an area, an x value range we are looking within. So we need a lower and an upper bound. That is our starting point. Now, what the algorithm does is we start in the middle of our x value range. And then we determine the corresponding function value, which is our y mid, and compare that with our target value. Now, in this case, we are too high. Since the function here is strictly monotonic, ascending, we know, okay, we are too high in our x value range. So what we do is we adjust the upper bound and give it a new value, which is the earlier middle point. Then we do the same again. We have our x mid, we have our y mid, and in this case we are too low. That means we have to adjust our lower bound upwards to our previous x mid. And then we do the same. And we repeat this over and over until we have reached a stopping condition. So in short, we get our x mid. Then from that we determine the y mid, compare that with the target value, adjust the lower or upper bound correspondingly, and then we just repeat this until either we have reached a limit for our iteration count, we have gotten close enough to our target value, or potentially when we're working with fixed point operations, we have no range left. And that should be enough theory about binary search for the moment. If you're interested in more details, I also talked about binary searches in episode 68 about lookup tables. You can find some more information over there. Nevertheless, it's time to show you how you can implement something like this in Minecraft. And here we go. Now for this example, I'm going to use emulated fixed point operations. So if you haven't watched my video about those yet, I would recommend to do so beforehand, or you might get a bit confused in the following. Nevertheless, I do have 3 functions. The first implements f of x. The second initializes my inverse binary search, and the last one is the actual recursion for the inverse binary search loop. So let's start at the front. So we have our function, and here I'm implementing x cubed plus 2x. This function I'm calling with macros. So during the function call, I'm giving it the name of the x variable to use and the scalar variable to use. This is just so it's a bit more variable in use later on. I'm also not directly implementing the function as is. I'm factorizing it beforehand. So I'm first calculating x squared, add 2, and then multiply with x. With the proper scaling factors, this is x squared divided by the scaling factor plus the properly scaled up 2, and then multiply with x and rescale again. So very simple indeed. And this is then just straightforward done. So x times x divided by scaling plus 2 times x divided by scaling, and that is then returned. And now it's time for the more interesting part, which is the binary search itself. So this here is the function we need to call when we want to trigger the binary search. And here I implemented it using macros. So during the function call, I'm giving it the target y value. I'm giving it the lower bound for my x value range, followed by the upper bound for my x value range. Then we have an optional limit for how many loops or iterations I want to go through. If this is set to 0, then it just counts how many loops it went through until it hit any of the other stopping conditions. If it's a positive number, then it will actually just go up to that number of iterations. And then we have finally an accuracy limit. So how close do we have to get to the actual y value we're looking for before it stops? Following that, we have preparations of the variables we need. So first I prepare my objective and set the display for it. That is somewhat optional. Then I write the y value and the various bounds into the corresponding variables, prepare the scaling factor, and just a factor 2 later on for further calculations. And then, for the rest of the calculations, I am assuming a positive slope of the function. If that is not the case, what I'm simply doing is invert the order. So I make the lower bound the upper bound and the upper bound the lower bound. Pretty simple stuff, actually. Now, that means we are going to start over here with first calling our actual function for, in this case, the lower bound and writing that into a variable which is called lower y. And then I do the same for the upper y. And then I just check if the lower y is greater than the upper y, which would indicate a negative slope. And then I just invert the lower bound and the upper bound for the x values. And while I'm there, I'm doing the same for the y values. Then I do some validity checks. I'm checking first if the y value we are looking for is not lower than the y value of the lower bound. So too small. Or higher than the y value of the upper bound. So basically I'm checking I'm within the range. So if it's not the case, then I'm just returning a failed value. Then I call my actual binary search and then return the result of that binary search. That is all of the initialization and pre-checks. And now it's time for the binary search itself. Now this is called again with a macro, but since this is only repeating here the accuracy limit, you could also alternatively just write this into a variable beforehand and then use that instead. Now the first step we're going through here is calculating x mid, or in this case temp result. So we take the lower bound, add the upper bound, and divide by 2. Then we check whether we have no range left. That means either the lower bound or the upper bound is the same as temp result, and in that case I return 1. So we have return, which stops the execution here, and we have stop condition 1, so return 1. This is not really used later on in the calling function, but if you want to expand on that, that might be useful potentially. Then we have the next stopping condition, which checks the loop limit. So first we decrement the loops bound by 1 and then check whether it's 0, and in that case we return 2. So stop again, stop condition 2, return 2. If this was set to 0 in the beginning, then we are just negatively counting the loops. So if we at the end have a loops bound of -10, then we had 10 loops in the beginning, or as a whole. If none of those conditions hit, then we check the actual function value. So first we call our polynomial with temp result as the x value and write the result into the temp y value. Then we compare that with the target y value, and depending on whether we are too high or too low, we adjust either the upper or the lower bound. Then we check whether we have hit the accuracy limit. So here I subtract target y from our temp y. That is now the error we're making. And then I check whether we are within plus minus the accuracy. And if that is the case, then again we have return and stopping condition 3, so return 3. If none of those conditions were hit, we continue with the recursion. So we call the same function again. And now it's time to show you this in action. So here I'm going to call my inverse function with multiple different input values, starting with a y value of 135 with x between plus and -10. Again, remember scaling factors are 1000 here. I'm setting no loop limit and the accuracy is 0.001. And we would expect a clean 5 as a result, and that is exactly what we get down here, also in the temp result, which is not a surprise. And the loop bound tells us this took exactly 2 iterations. Now, y value is -135, the rest is the same. Expected value is -5 since the whole problem here is symmetrical. And that is exactly what we get. Also over here, again, just 2 iterations. Now, for the next example, I'm going to first start with a cleanup. And now we have a y value again of -135, but x is between 0 and 10. And that means we are out of bounds, and that means we get a returned 0, but this is actually a failed 0. So if you check for the success of this operation, it actually tells you that this failed. Over here, you can also not find any temp result since no calculations were even started. Then clean up. Next example. Now y is just 130, and the expected result is roughly 4.934. And yeah, that is exactly what we get. But this time it took about 15 iterations. So a little bit longer. Now I'm going with the same calculations, but now the accuracy is 10 times of earlier, so 0.01. And in this case, we are somewhat lucky that we get the same result, but we could be basically anywhere between plus minus 0.009 with this calculation here. Now accuracy 0.1. And now we start to see a little bit of a difference, but with this accuracy, we could be anywhere between plus minus 0.099. And then finally, now accuracy is 0.001 again, but we have a loop limit of 5. Remember, earlier we used quite a bit more iterations. And if we do this now, you can see, okay, loop bound is 0 since we started at 5 and went down. But the result is quite a bit different than what we would expect. So limiting the loop number can be quite a problem depending on how big your original x value range actually is. So be careful with limiting the loop number. That can very quickly lead to very inconsistent results. And with that, we've reached the end of this episode about using binary search to invert a function. I hope you enjoyed this episode. I wish you a nice day, and well, see ya.